Summarize chapter 5 a little bit. So in this chapter we extended the idea of separation of variables to a few more non-trivial examples. So in particular we now looked at a case with Robin boundary conditions, and we extended the spatial domain to a two-dimensional spatial domain. For the Robin boundary conditions, you might remember that we had to solve, well, as we looked for the separation variable and then found a condition for solvability, we got to a strange equation which was this: tan of mu L equals coefficient kappa divided by mu. And so then the eigenvalues would be all mu that solve this transcendental equation. And what you then need to be able to do is you need to be able to plot. So tan of mu L looks something like this. This is the tan function. You can do this much nicer if you use like Desmos or any computer program. And then the other function, kappa divided by mu, is just a hyperbola going down. Right? This is kappa divided by mu. And then you find a whole bunch of intersections here. And these are possible solutions for that equation. And so then you call them mu1 here and mu2 here, mu3 here, etc. So this happens whenever you use Robin boundary conditions. You can have other boundary conditions, and then of course you can imagine all kind of stuff can happen. So eventually you end up with a transcendental form equation, and then using a graphical method to solve it is always the best. Then secondly, we talked about the D'Alembert solution. We can derive it from many different ways, for example, method of characteristics, etc. But in this chapter, we derived it also from the separation idea. And D'Alembert solution is a very, very powerful method. Okay, coming to higher dimensional problems, where we have u of x and y and t, then we saw that we have to separate all of them out. So we can do x of x, y of y, t of t, and then you write down the time equation and the x equation and the y equation, and you separate the boundary conditions also accordingly. What you then find is you find problems for two eigenvalues, right? You find two eigenvalues, or I should say two eigenvalue sets. So maybe what did we call them? Lambda nm equals alpha n plus tau m, where let's say the alpha is from the x problem and the tau is from the y problem, and together they form a class of eigenvalues which have two indices n and m. And correspondingly we have eigenfunctions which are combinations of the xn and the ym. Okay, so this sounds complicated, but it isn't really. The main part is that you do a careful bookkeeping. You just need to keep track of all the indices n and m, and then if you can do this, then you will be able to master these type of problems.